So one of the things that you may be aware of related to Earth's magnetic field is that we have magnetic reversals. What that means is that over periods of hundreds or thousands of years, the magnetic field periodically reverses polarity, becoming the South Pole and then vice versa, hence becoming the North Pole. So during a magnetic reversal, the magnetic North Pole becomes the magnetic South Pole, and then back to becoming the magnetic North Pole. So lava that solidifies during a period of reverse polarity is magnetized with the polarity opposite that of volcanic rocks being formed today, which is a normal polarity. So when the rocks exhibit the same magnetism as the present magnetic field, they are said to exhibit normal polarity. Okay, so currently we are in normal polarity, and if the rocks exhibit the opposite magnetism as the present magnetic field, we refer to this magnetism to be having reverse polarity. So we're not sure why the magnetic field changes polarity, and it does not do it periodically, meaning those reversals appear to be random, even though on average from the last 5 million years they seem to have happened every million years or so. So even though they happen, we have no idea why, and they are not doing so at a rate that can be traced, meaning it's random in terms of years that they reverse. So once it was understood that magnetic reversals happened, researchers set out to establish the magnetic timescale. Meanwhile, oceanographers started to also test the magnetism of the ocean floor using magnetometers. So the first study of this kind was done in the Pacific coast of North America, and alternating stripes of high and low intensity magnetism were discovered, as you can see on the image here on the lower left. So this is the stripes basically. This is how it's done with the magnetometer, what you're going to find high polarity and low polarity times, and they correlate with the stripes that are found. This is more alike what you would actually find with a magnetometer in the ocean floor. And it was Fred Vine and D.H. Matthews who demonstrated that the high and low intensity stripes supported the concept of seafloor spreading, basically. So these two guys, Fred Vine and D.H. Matthews, suggested the stripes of high-intensity magnetism were regions where the paleo-magnetism of the crust exhibited normal polarity, meaning what we have today, or similar to what we have today. Which means that these rocks enhance, or rather they reinforce the Earth's magnetic field. And conversely, strands of low intensity, so these low valleys, if you would, within the record, are going to be regions where oceanic crust is polarized in the reverse direction and therefore weaken the existing magnetic field. All right, so Vine and Matthews reasoned that as magma must have solidified at the crest of an oceanic ridge, so it must have solidified near this top part of the ridge, and it is magnetized with the polarity of the Earth's magnetic field at the time of crystallization. So because of the seafloor spreading, this strip of, let's call it normal polarity, a magnetized crust would gradually increase in width, this one right here, right, as it's doing, it's gradually increasing in width with further material coming up until the next polar reversal. So in the next polar reversal, when any new material started to rise up to the surface, it would now have a reverse polarity. So it would be kind of like the tan colored one growing in between there on the crest, and would appear again right in between the previously normal polarity magnetized material. So this reverse polarity new strip that would continue to thicken with further material rising further and further, and it would thicken as seafloor spreading continued to occur. It would only be stopped until the next polar reversal. when, as new material crystallized, it would now have a normal polarity that aligned with current Earth magnetic field, right? And so normal polarity magnetized material would then form, thicken, and then only stop until the reverse polarity event occurred. So this can also be seen on the top right of the slide here. Because new rock is added in equal amounts to both trailing edges, right, of the spreading ocean floor, we should expect the pattern of stripes, both in type of polarity and in width, to be a mirror image of those on the other side of the spreading of the mid-ocean ridge. And this particular thing is indeed what we've been able to see in the different studies that have been carried out. We've seen a mirror image like the one that is proposed here on the progression of this image on the top right of the slide. So based on this understanding and using radiometric dating, geologists could therefore infer the ages of the ocean rocks. And it's been found that the ocean floor is no older than 200 million years old, with those parts that are oldest being here in blue on the image that you have. So oldest ones are in blue, and then they get progressively younger as they get towards the red areas. So just as a summary, what occurs is that, again, rising magma at the ridge is extruded. Then you have cooling rocks that are magnetized. Extruded magma pushes those older rocks away from the ridge, and eventually the magnetic field is reversed. And as new rocks are erupted with the new reversal, a record of different polarity remains for that time period of reverse polarity. And as this pattern continues, it happens over and over with changing polarity, seafloor spreading can thus explain the stripe pattern from the strong and poorly magnetized rocks that appear as mirror images from the mid-ocean ridge, like what we actually saw over here. So this would be a real world example of that record. So here is just the image that was in the last slide, blown up a bit for you to appreciate the ages of the ocean floor based on those dating techniques. So you can go ahead and pause the video for a bit if you'd like to look at it further, or you can go ahead and look at it in your book as well. So one of the last pieces of evidence that allowed scientists to recognize the theory of plate tectonics and that it was actually valid was the existence of hotspots. And this evidence line also came about by the observation of features from the seafloor mapping that was done. So a hotspot itself is an area of volcanism with high heat flow. And here in this area, you're going to have crustal uplifting that is a few kilometers across. This type of volcanism is typically unrelated to plate boundaries. So in hotspots, or I should say hotspots can occur in between the plates. They don't, in fact, they almost never happen at the boundaries. They happen in between the plates. So far, again, I've told you that volcanism occurs at or near plate boundaries. For example, the Cascade Mountains or the Andes or the Aleutian Islands or things like that. Near seafloor spreading also, or rifting. So for example, those volcanoes that we see in the near the Horn of Africa area in Ethiopia, Uganda, and whatnot. Or between tens and hundreds of kilometers inside the plate that is not being subducted at a subduction zone. So again, that would be things like the Cascades. However, you can also get volcanism at hotspots, and how that works is much differently than it works at plate boundaries. So one widely accepted hypothesis, it's not a theory yet, but it's a hypothesis, and it's widely accepted, proposes that a roughly cylindrical shaped upwelling of hot rock, typically that is coming all the way from the asthenosphere, and we call it a mantle plume, as you're seeing here on the bottom slide. This would be the mantle plume. is located beneath the surface expressions, which are the hotspots. So this would be the hotspot. This is the mantle plume below, which is that hot, roughly cylindrical, upwelling hot rock. So a good example of where a hotspot is and was, I guess, are the Emperor Seamount chain and the Hawaiian Island chain, which is what you're seeing here. So here we're only seeing the Hawaiian Islands that are above surface, but this expression, this hotspot expression, is linked to a much larger set of islands and seamounts that are below the surface and further away. So the mantle plume that is currently beneath the Big Island of Hawaii did not always appear under the Big Island of Hawaii, but as the Pacific Plate moved towards the north and then towards the northwest, the hotspot itself changed from being initially at the Troit Seamount, which is actually all the way near the Kamchatka Peninsula in Russia, and it started making a track towards its current position, somewhere in the semi-tropical region of the Pacific Ocean, pretty much in the middle. I should also mention here that a seamount is basically a volcano that perhaps at one point was above the surface, though not necessarily, but that it is no longer active and has been eroded and has been submerged if it did ever make it above the surface of the sea. So again, just to be clear, mantle plumes, which remain stationary relative to the Earth's poles, can appear beneath both oceanic lithosphere or continental lithosphere. But it is the overlying lithospheric plate that moves on top of the plume, which causes the surface expressions, which we call the hotspots. So to change locations as the plates move, this will cause a linear track typically that we see expressed again as seamounts and volcanic islands like the Emperor Seamount chain and the Hawaiian Island chain, or like volcanic cones or calderas if they appear inside continental areas like we see in the Yellowstone hotspot and its previous track, which extends through much of the eastern Snake River Plain, for example. And we'll go through both of those examples in the next few slides. So from the picture of the Hawaiian Islands, you see that Kauai, which is the oldest island, right, formed 5 million years ago or so. And when it was positioned over the mantle plume, it was the only modern Hawaiian island in existence. Kauai's age can be dated, obviously, as we have done so, but it can be seen by the amount of erosion that is apparent in contrast to the fresh lava flows in the Big Island of Hawaii, for example, that it is much older also, not just from the dating. One of the cool things from the hotspot tracks is that you can use the age of a volcanic feature and the distance of it from the hotspot, from the current location of the hotspot, to determine the direction and also the rate of the plate's motion. So if you look at the image above, you can see the clear change in direction that the Pacific Plate had about 40 million years ago. So this image right here is actually of the seafloor. So you see that this is the chain of Emperor Seamounts, right? And eventually the change of direction happened here. This image right here actually shows you the ages. So again, Detroit Seamount is all the way up here near Kamchatka Peninsula. And you see that about 40 to 43, I guess, million years ago, the Pacific Plate was not moving completely north, but it started moving northwest, which is what caused the change in direction in the hotspot expression, as we're seeing there. So the same thing that we saw for the Hawaiian hotspot happens for the Yellowstone hotspot. So the mantle plume that is beneath the North American plate currently, initially beneath southeastern Oregon or northern Nevada, as you can see over here, about 15 million years ago. And as the North American plate moved towards the southwest, relative to the mantle plume, the hotspot has migrated towards the northeast, further and further through the eastern Snake River Plain, and it now lies here in northwestern Wyoming, where the last eruption occurred about 0.6 million years ago.